But yeah. Okay. So now we have planned for today a little bit higher. Okay. Yes. So we will speak about computation with Oracle. So we will think about what if we have special power to solve a difficult problem. So for programming, like in Huawei, they have to solve many optimization problems. And so they run SAT solver or constrained programming solver or whatever solver. It takes a problem for an NP and gives an answer. And so we can think, what if we can ask a few questions like this? Uh, or one can think like maybe someday in the future, people will build quantum computer. So it's a kind of new device. What if normal computer can ask questions to quantum computer and get answers? So then all the classes changes and we can model it with Oracle computation. So A is a language, and we will define the class P with Oracle A. Oh, you need, I will not change it, just P with the power A. And so for this, we use Oracle Turing machine. So there is a computation head as usual, but now there is an extra Oracle tape. And so the machine can compute and write a string to the Oracle tape and then ask the Oracle, please tell me if it's in the language, yes or no. And the machine answer within one computation step. So that's the model. So Oracle tape. And then we have the usual work tapes and one of them contains the real input. So the usual thing. So let's do a few observations. So we say that B, sorry, I didn't write the definition, but it's kind of the definition of polynomial time is now the same. There should exist. So B is in polynomial time with Oracle A. If there exists a machine that decides B in polynomial time using questions about language A on the Oracle tape. So note that if it gets a word W, an input W, it can compute a long time to ask a question that is longer than W on the Oracle tape, but it should be of polynomial size into the W. So let's do an easy question. If we know that B is in P to the power A, can we say that B is in polynomial, can we say that the complement of B is in P of A? So it's easier question, of course, because we can just flip the answer. It's the same without Oracle. And so when we know the answer, we can flip the answer. We can flip accept and reject state. Another question. Do we know that B is in the complement is with C. So do we know that B is in complement of PA to the power C? Yeah, of course, yeah, indeed. We just flip Oracle answer. Now imagine that B polytime reduces in A. Do we have that? Sorry. if B polytime reduces to A, can we say that B is in PA?
Yes, because we apply the reduction and then we just then we run the algorithm for A, but it's just one step. So
Yeah.
the polynomial reduction is the entire algorithm.
Yeah. So here, so our algorithm that uses Oracle A will ask one question to the Oracle, and it will be the question, is a string into B? But we need to, it's easy, nothing needs to be done. Okay. And now, following question. So, our first task is NP in P sat.
Yes, because that is NP complete problem. And
Yeah.
then we use this lemma.
Exactly. And so for every B in NP, we know that P reduces polynomial time to SAT. It's definite by definition of NP hard. SAT is NP hard. So so since B reduces to SAT, B is in P with SAT Oracle. Okay. So there exists a class co-NP. It's the set of all problems whose complement are in NP. So all the questions. For example, given two circuits, do they compute the same function? So circuit equivalence, it's called. And this problem is co-NP complete. So why is it true? I think it was exercise in one of the previous exercises. So there are two circuits. And then the question is, for all input factors, so for all bit factors of the correct length, is phi x equal to psi of x. So this problem is in co-NP. And so we know that circuit equivalence is another problem that is in PSAT. So this problem is in PSAT because it's in co-NP. So note that definition of NP is not symmetric. So we have computation tree, string is in NP, string is in the language if there exists an accepting leaf, but string is not in the language if all the leaves reject. So it's not symmetric, and the question whether NP is equal to co-NP is a big open question. So if P equals NP, then NP equals co-NP because P is closed under complement. But this is open question, and also you can break a lot of cryptography if it turns out to be true. So
Just if NP equals co-NP.
Yeah, just NP equals co-NP, then NRA, or how it's called. So public key crypto, RSA, yeah, is so you can break it. So you can factorize numbers. We discussed it at some time. And no. Oh, so sorry. I'm sorry. This is other assumption. So if this is equal to P, then you can factorize numbers in P. Okay. Sorry. So, but this is also open question whether NP intersect. So it can happen that NP is equal to co-NP, but this and but both sets are equal, but they're still bigger than P, which is also possible. Okay. Yes. So I will keep circuit equivalence problem for our next task. Let's first define NP with Oracle A. So, and I think you can guess the definition, right? So now we have non-deterministic machine that decide the Oracle, and the non-deterministic machine can ask questions to the Oracle. And so circuit non-minimality, so the question is as follows: you get the circuit, and the answer is yes, if there exists a smaller circuit computing the same function. So having the same answers on all inputs. So let me write it. And the claim is that this is an NP with Oracle set. So while I write it, you can think how the algorithm goes. So what algorithm is doing. And so just we have a computation tree, but now in the tree we can ask questions to the Oracle. Non-bin for the input. Okay. Things is smaller. So the size of circuit is number of gates. With pi input circuit phi is our smaller circuit psi that gives same replies on all of the axes. And the claim is that this problem is in NP with Oracle sub. Okay, so I actually did we prove that this is in co-NP? Okay, I'm again retarded. So did I already prove it? It's clear how to prove it. So we have to check whether the complement is in NP. So the negation of the question, there exists X for which answers are different. It's clearly an NP because this special X where answer different is certificate. So this is in co-NP. So that means that complement of this problem reduces to complement of set. So this problem is reducible. Only time reduces to complement of set. Okay. So now it's clear, right? Why this bottom problem is an NP with Oracle set.
Because NP with Oracle set is the same as NP with Oracle set.
Yeah. Yeah. So non-deterministic machine will guess smaller circuit and then ask the Oracle whether it's complete. So the computation tree, every leaf will ask a different question to the Oracle. And then if the circuit is indeed minimized, then every leaf will, so every smaller circuit will be not equivalent. And so the machine will reject. But if there exists smaller circuit, then the leaf that guesses the circuit will accept. So it's an NP style. Okay, so it went very smooth. Any questions? Oh, we have property is just about complement. Well, here we have. So we prove this. So more in general, if A is X complete for some class X, then we have that X is a subset of PA. Yes. Okay, no problem. So this is general. So we will use this in a second for the class X. So X complete means that problem is in X and every problem in X reduces to the problem. Okay, so these are all done. And now we go to main result of today. So there exist special oracles. So later it can happen that physicists invent new computation device and P equals NP as reality. Or we can prove that P is not equal to NP. And so this is this will be kind of not too hard proof. We will prove that we can take any X complete language A and both classes are equal. So I will explain it soon. So here we have to use diagonalization argument. So this works by diagonalization. And that means that every proof that settles P versus NP question that is diagonalizable, so that you can, so almost all proof techniques, a lot of proof techniques, they are diagonalizable. So whatever you do with the proof, you can do it with an oracle. And so this is diagonalization barrier. So if somebody comes with a proof, then the first question they will ask, which step breaks diagonalization barrier? So which step of your proof you cannot do with an oracle? So if proof is just diagonalization, then you know that proof cannot work because every diagonalization proof is diagonalizable. So yeah, so that there are like 5 barriers to prove it. And that's why many specialists not even bother to think about P versus NP problem. Although it's a good idea to think about. Well, I never had time for such thing, but they say it's a good idea, but there is no, there are too many barriers known. So if somebody, and every few years, somebody invents a proof to go against around all the barriers at the same time. And so then a few months later, somebody invents a new barrier. So it's how it usually happens. Okay. So yes, let us go to these 2 results. So first, let us have some lemmas. We don't need this anymore. So first, I claim that if A is an X, then X is a subset of Px. So this is kind of easy lemma, right? So can you say why it's true? So if we have a language in X, oh sorry, that should be with oracle.
Computation here complete.
Yeah. Okay, let me first
But if A is
yeah.
complete, then it's
Yeah.
that lemma region.
Yeah, it's again the same thing. Yeah, I already explained. Okay. Yes. Let me write the first theorem. So A is X complete. Then EA equals NP. And so first step is already clear. So assumption, so A is X complete. So we have that X is a subset of EA. So this is okay. And now we have to prove. Okay, what will I? Okay. Now the second step, I will prove that NP.
Want to prove that each A equals X?
Yeah. So now I want to prove that NP to power A is a subset of X. So if we prove both these things, then we are done. So it's readable at home. And the first we already did. And the second one is true for every language in X. So here we don't need completeness. So here for all A and X. Let me write it better since we have a bit of time left today.
Because we can run all the branches.
Yeah.
This at the same time, and so there are at most 2 to the power of polynomial branches, and X is, if we take, so it would have,
Yeah, so what's the plan? We will go through all of the computation tree, but from time to time we have a question about Oracle A. But we know that A is an X, so we can run the decider on A. And now we just check that going through all of the tree is done in exponential time. Okay. Well, so first step, imagine that the answer come in one computation step for A. So we will do first ignore the time to solve A, well, this Oracle questions, and then we will count the time because they both are linked. So size of the tree is computation tree was 2 to the power of 3 has size at most 2 to the power, yes, polynomial P of n, where P of n is bound on runtime of non-deterministic machine. So in each step, we split in at most 2 branches. And so number of nodes is at most 2 to the power P of n. So in each computation step, we have about +1 to be precise. Okay, but it doesn't matter. It just, yeah. So number of nodes in the computation tree is at most this thing. And then, going through the tree is polynomial in this number. And now we have to think about the questions to the Oracle. So for this, we need to think about how much information is there on the tape. Because our language A is in runtime exponential in what is written in the length of the tape. But the machine works in polynomial time. So maximal size of a word on the Oracle tape will be P of n as well. So number of queries is at most number of nodes in the computation tree. And so runtime is some polynomial of size of 3, 2 to the power P of n for the computation, plus time needed for solving Oracle queries, times and then 2 and some other polynomial of n, well, Q of P of n. So Q is time to solve A. So 2 to the power Q of n. Well, yeah, so, but this is different, and it's input of the word on the Oracle tape. Okay. Runtime poly. So, and this is still polynomial. This is 2 to the power. Some large polynomial, but it is so this is in exponential time. And so we have proven this thing here. And so this is proven now.
if we know that there is an X complete.
I always, yeah, good point. I need to give you an extra complete language. So not yet. And so language will be pair of a description of a machine and a number n in unary.
In such.
Yeah, exactly.
That's a general error, right? With language which is given a machine and.
No, wait, I should give it an input. W terminates or accepts in time 2 to the power length of W. So this will be NP complete language. So this is our next lemma. X complete lemma is
Starting to choose the same as for B complete. No, not B. We have something. We proved something similar.
just a moment ago. Okay, so now we have to prove that every language in X reduces to this language. Okay, and this goes by padding the language because of definition of X. So it seems you're a bit too fast. So here, what is X? The runtime should be 2 to the power poly of n. But here we have the machine can run in time 2 to the power length of input. So the time is too short. But we can artificially increase the length by padding it with zeros, with 1 followed by many zeros. So there were several exercises in seminar, and I forgot maybe one of them was in the homework. So what is the plan? Okay, so let us take a language B inside X. And now we have to build a reduction to this language. So let us call it exponential half time or exponential acceptance, exponential time acceptance. So this language, and so we have to build a reduction, a polytime reduction from B to exponential acceptance. And so the plan is, okay, so B has decider. So M decides P n times 2 to the power P of n. So let's give the polynomial the name B. So in polynomial P, B of n runs in time. Okay, so now we will map where W. Well, it's still, yes, it's still readable. We will map it to W followed by 1 and then followed by zeros. And so how many zeros we will use? That is PB of length of W. So that's the plan. We make input artificially longer. And now when we give it to this language, when we, okay, so we know that this string, so, sorry, and I need
which machine
as well. Yeah, I didn't say the machine. So
well, the machine decides with the prefix and then just
so this
ignores.
yeah. So we will use this M.
No, not really this M, a big change. We need a machine that
That ignores. Yeah. Sorry.
The prefix, the signs.
Yeah.
And
Okay, I need to
then bar.
write some tilde. Yeah. Tilde. Okay, so what we do here, we don't run the same, there's just machine M tilde takes the input, then chops off this the final zeros and this 1, and then simulates machine M. And so now, okay, and let us use also the W prime here, a different letter, so we can compare more easily. So when we ask whether this is in our EA language, then we apply the definition. But now we have a W which is much longer than W prime. So how long will this machine, is this machine allowed to work? Well, it's allowed to work length of W prime plus PB of length of W prime.
Same, but
Yeah. So polynomial in length of W prime, which means that it exceeds the runtime of M on W prime. Because of all the zeros, this W, this length is artificially longer, made longer, so that the exponent becomes much bigger. So, but it's still polynomial time reduction, because to W prime, we just append a polynomial amount of zeros, but it helps tremendously with this bound. And so we made reduction from B to our language EA. And that means that this is X complete. Well, it's clearly an X. So it's XP hard, we just proved, and it's clearly an X because we just have to simulate this machine for exponentially many steps. Okay. Yes, and now we are done here. We have proven that when we use EA for this language A, we have P is equal to NP. Okay. And now the hardest result of this lecture. So I already explained about diagonalization barrier, and complexity zoo is just, we will speak about all the classes we've seen so far. And that's just some blah blah, you don't, well, good to know, but nothing difficult. Okay, so now let me make some space, and then I will write down construction of B. So note that we just have to write, there exists a language B. So this language can be harder than the halting problem. It doesn't matter. The claim is there exists some B. So I need two things to prove this. I need the language B in the oracle, and then I need a language that is in NPB, but not in PB. So I need a second language to construct. And I will first say, what is this language? How we get this language? So after we constructed B, it will be a unary language. So we will have, so I will define a language LB that depends on B, and it's defined by, it contains all 0 to the n, for which B intersects for which B contains an n-bit string. So LB, language for which B contains at least one string of length n. So now I claim that LB, for every language B, we have that LB is in NP with oracle B. So why? Readable. Okay, I should write a bit bigger. Oh, and I didn't hear anyone from home, so I put you extra loud so you can speak. Okay, so LB is in NPB. So remember the definition. So almost by definition, it's true. So
we just check every string of length n if it's in B, and
Yeah, so we need a non-deterministic machine that runs in polynomial time, but it can ask questions to B. And so you say certifier definition. So he says, okay, let's interpret certificate as a string and check whether this string is in B. Very simple. You
Okay.
just try to guess the string in the intersection. Or non-deterministic machine tries to guess, and if there is one in the intersection, and if Oracle says, yes, I have this string, then it accepts, otherwise it rejects. And so if there is intersection, then a non-deterministic machine accepts, and otherwise it rejects. So it's almost by definition. Okay, so on this front, we are good. Now we want to prove that so we want to say that there exists a B such that LB is not in B with Oracle B. Okay, and so here I will use binary language for B. So let us make some drawing. And these are, so I'm drawing the language B. So we have some binary tree. I will just take some time to draw a little. And so what is LB? So here it is the empty. Then we have 0, 0, 0, 0, 0, and then 0, 0. Okay, and as usual in diagonalization proof, we will start with the list of machines. Yeah. So let's make machine 1, machine 2. They are just all the, so here we have a list of all polynomial time Oracle machines. Only time. And so you cannot compute a list of machines that run in polynomial time. So our construction, we cannot compute it, but it doesn't matter. We just need one B. It doesn't need to compute it. So we make a list of all the machines. And now we will make sure that machine 1 is run on strings of length 1. Machine 2 on strings of of certain length. We will pick a length later. And this will be a fast increasing sequence of length. So we will choose, okay, so we can choose N1 equal to 1, but N2 will be much larger. And 4 and so on. Okay. And then what is the plan? Oh, actually, sorry, and 1 is not equal to 1. Some number, we will pick it later. Okay, and so what we do is, now we need to decide which strings are in B. And the plan is when we start working on the machine M2, we will block our answers. So we will change our answers all the time on B, but at some moment we will block the answers for short strings. And this is to ensure that our answers on previous machines are always wrong. So, okay, this is philosophical, let me just say the construction. So what we do is we run machine 1, and if it asks an oracle to the question, we always say no, 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 no. And then M1 runs in polynomial time, so the machine stops and says the answer, accept or reject. When it says accept, we do nothing. And we look to all the questions that machine M1 has asked, and we say, look, these are the answers. It asks for strings of length at most this thing. And so we seal off these answers. And so we run M1, so let me say it. So algorithm run M1 on, let's say, empty. So M1 asks questions, we say no, 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 no. If M1 says I accept empty, then we do nothing and we seal off the strings. So we look to the longest question he asked and we block. Now forever, the set B will not contain any strings of this length.
Hmm.
So that the machine is wrong. What if machine M1 says I reject empty string? Then we will, no, empty string is not a good. Oh, yeah, then we add empty string to the length. So here n starts, okay, let us start from M0 in case that's it. No, it's okay. And then we say, so if it rejects, then we say empty string is in the language. And then we do the same thing. We look to N1 and seal off the language B, so that and we promise to make only changes to B on strings of larger length. And then we repeat the process.
So ground N2 on 0 repeated N1 times.
Yeah, and one, let's say N1 plus 1 or something. Okay, yeah, we can say N1 is at least one more than the biggest question that was asked. And then we indeed ask, we look to the string 0 for M2. We look to 0 to the power N1. So the string with N1 zeros. And then we run the machine again. So when it asks on previous strings, for example, if it asks about the empty string and we add it, we answer consistently. But if it asks about the string that's larger than length N1, we didn't make a decision yet. And then we say no. All the time we say no until we get an answer. If it says accept, we are good. And we seal off all the strings of length that were asked by M2. So we look to the maximal length of the Oracle query, and then we add and we block this, and we set N2 equal to 1 more. And so we go to M3. And then we repeat. So each time we seal off, we make sure answer of previous machine cannot be changed by blocking certain threshold. And then we make sure the next machine is wrong. And so it's diagonalization argument. And so when we give it some n here, so imagine that this is whatever n5. So we run the machine, it asks questions on the oracles. We say no. And then if machine rejects and 5 zeros, then we select 1 and we say it is in B. So we add it to B. So about definition of n, I forgot to say something. We need extra condition because maybe a machine M4 runs in time with a huge polynomial and it has enough time to ask about all the strings of length N3. And so we said no on all of them. And then, of course, when we add a string, we must add one that was not asked before. So there is mathematical problem, but it's not a big deal. So you understand why. Well, we just need to increase N3 further because how many strings are there of length N3? 2 to the power N3, right? But the machine runs a time polynomial to the power N3, polynomial in N3. So if we increase N3 further, we have that there are more strings than he can ask about. So this plan of machine M3 to ask about all the inputs of a given length, it will break after a certain constant. So now let me say it again because I forgot about this extra constraint. So what we do? After we run machine M2, we look to the largest query N2. Then we look to the polynomial bound on the runtime of machine 3. Then we increase N2 further so that this polynomial bound is smaller, much smaller than 2 to the power N2. And then we run the machine. And so when it says I reject, then we know it cannot have asked about all the strings of this length. So we can add one string that it didn't ask about, and then adding it will not change its answer. So, and that's the proof. So we can repeat for M3 and so on.
At arbitrary string of the given level.
Yeah. Well, arbitrary, so we add a string, but of course we cannot add a string that he asked in the oracle, because then we change the computation and it might no longer be wrong. So that's the plan. Well, that's the proof actually, because nothing more needs to be done. And so we know now, okay, no, let's just finish. So after this construction, we know that every machine gives a wrong answer about this language LB. But here we made a list over all Oracle Turing machines that run in polynomial time. So that means every polynomial time Oracle machine makes a mistake. And it means that LB is not in P with Oracle B. Because of definition. If it was in P with Oracle B, there was Oracle time that solves it with questions to be in polynomial time. Just by definition. So it's very natural strategy. Write all the machines, make sure first one is wrong, second one is wrong. And each time we understand the machine is wrong, we increase the length and we do not change the answers on the computation that where the machine made a mistake. Okay, it's hardest proof of lecture. And we have half an hour.
Why one can not ask about all leaves of legs?
Okay, yeah. So what we plan. Okay, so I gave a bad example because I said let's run on the empty string and then it's only one string to ask. But this was not correct answer. Yeah, I should say pick N1 large enough. So M1 runs in polynomial time, runs in P of 1 on the input length N. So now we will choose N so that P1 of N is much smaller than 2 to actually strictly smaller is enough. And so strictly smaller than 2 to the power N. So that's good. Let's choose N1 such that this is true. And then, okay, I'm like making mistakes with the indices. So I used N2. Okay, so yeah. So when we take such and now we will ask M1 about 0 to the power N1. So we should use the same in there. Okay, it's just a numbering a small issue. So we ask M1 about this question here. And then we answer no for all oracles. And then if machine accepts, we don't do anything. And we seal off all the strings that were queried. So we say, okay, biggest query was N2. And then we it was N2 minus 1. So from now on, we will only change for N2 or bigger. And then we look to the second machine. So its runtime will be about P2 of N. And we choose N larger than N1.
Larger than N.
Such
N2,
that
but
this is smaller than this. So we make sure, yeah, it's larger than. Yeah, I should have.
Maximal depth of.
Yeah. So basically, I need we choose N2 so that this is true and maximal query length of computation of M1 on 0. This is on the computation. This computation. Okay, so let me say it again. So there are 3 conditions. Well, let's write it. So I have some space here, I think. So there are 3 conditions of about Ni. First condition, it should be bigger than Ni minus 1 plus 1. Oh, let me write it like this because otherwise I have Second condition, it should satisfy pi and I strictly smaller than 2 to the power n I. And third condition is that it should be bigger than any query made and all the previous computations considered. So max query length. Yeah, it's still, yeah, it's hard to read. Max query length of M1, 0 to the power N1. No, I minus 1, 0, and I minus 1. Okay. So these are the three conditions. Bigger than previous, large enough so that the machine is slow enough and cannot ask about all the strings of length Ni. And third, bigger than any query made earlier. And then if we choose Ni like this, then we add strings so that the answer is guaranteed to be wrong. Okay. So we still have some time left. I can explain one more time. Oh, it's okay. And now we understand. So since every Oracle machine is wrong, we have this result, and we finish the proof.
Can actually replace polynomials with arbitrary function, which grows slower than exponential.
Yeah. Yeah, so you can make a version. Oh, actually, that's good homework question for next year or something. Yeah. So I can say about what quasi polynomial time and quasi non-deterministic polynomial time. Yeah, or even weaker classes. So log space. So I can
I'm sure there won't be problem with NP to the N, like if we take quasi polynomial class for like N could be will LB be in.
Yeah, but then you need to replace exponential time probably by other class. But I think in quasi polynomial time we're still okay. No. You need x complete, for example, and then it's okay. Yes, and so this is diagonalization barrier. So if you prove that P is equal to NP or P is not equal to NP, then we can run this proof, this construction, and you must say where in your proof this step fails. And one of the ways to do it is by introducing a circuit. So if your proof goes through circuits, then you have a lot of chances. So here we only use answers of A. But when we transform computations to circuits, then we cannot transfer answers of this secret language A into a circuit. The only thing we could do is consider Oracle circuits, but yeah, so but with a bit of luck, yeah. So I mean, it's a strategy. So then if there are proofs that say, look, we go from there to there, we only thinking about circuits, and that's where we break diagonalization barrier. So at least a good idea is to have this. But then there is, of course, the next barrier, algebraization barrier, natural proof barriers. So the next step is, there is a nice proof about IP equals P space. So in NP, yeah, so NP is class where we have certificates. But in P space, we don't know about certificates. So there's games, there's a game tree. but there exists something like interactive certificate. So the verifier can use some randomness and ask for a proof that depends on the randomness he's using. And it turns out that PSpace has such interactive certificates.
Direct certificates with the transient real time problem.
Yeah, that you can verify in polynomial time. It's in the end of Sipser book and chapter. But it's maybe more clear and well, no, and I don't find it clear either in Aurora Barak book. So, but maybe I don't know if you try both of them, but I think maybe easier in Aurora Barak. And I didn't check in nature of computation, but okay, most people learn it from Aurora Barak, and it's Alexander Shen proof. So he has written many books, so and some people know him. Okay. Yes. Okay, so now we will speak about all the classes we've seen. So
If we're about LB in and quasi-polynomial to be, we need this class to contain at least linear time of n, because we need to check every bit string of length n.
yeah, that's true. But log space is okay.
Log space. No, log time won't be okay.
No, log time is not okay, but log space, yeah, I was thinking about log space, so you can do something similar. And it's a
log space is not something because it's space and not time. So probably consider time relevance.
yeah, but if you have logarithmic space, you can count in the space to n. It's no problem. Yeah, but okay, the definition of oracle machine is a bit complicated. So you need a very special oracle tape, because in log space, you can only use logarithmic space, and then you could cheat with the oracle tape. They write something, and while you're writing, you remember about previous computation. So you need to have a machine that can only write once and only move right, and then write some special symbol to say, I'm finished writing. Then get the answer, and then either the string disappears, or you can only go right and write the next string. So something like this. Yeah, that's how I would define it. Just write on oracle tape special symbol, and then only go right afterwards. Yeah. This is dangerous. Yeah, dangerous stuff. So very good remark. Yeah. Okay, so now let us speak a little bit about all the classes we've seen. So there is, so let's make a change of all the. We have here. So the class B, well, there is a class L, I will write it later. So we have NP. We have P space, and we have X space. Okay, and so there are open questions, so nobody knows. So they're all inclusions, and many people think that they're all strict inclusions. So in practice, so if class is an NP, and then it's in practice, it's either in P or NP complete. So the exceptions are problems in crypto and graph isomorphism. So there are very few other problems that are in between, or believed to be in between. Okay, and then there is polynomial identity testing, which is so probabilistic classes. There is a conjecture that it is very close to P. So people are kind of close to the randomizing, but they don't know yet whether probabilistic polynomial time is. That's the topic of next lecture. But okay, why do I say this? Okay, so if you have industrial problem, it's usually NP complete, and you can solve it with one of the solvers, but you need to do a bit research. You need to help the solver a bit and clean up everything, and then so it means some work, but in practice it's possible. However, if you have adversary, he can generate problem from crypto and break your solver. But in practice, so real problem that makes money is not from cryptography. So set solver works. So in practice, they're kind of equal. So here we have the problems where we can check solution. If there is if you can back all the routes of some optical network, or if you can schedule all the tasks in CPU nicely over the course. So this can be checked. Then there is NP is in P space. So here many games, they are either P space complete or X space complete. Like generalized chess, generalized Go. Chess on 8x8 board, it is finite game. So there are finitely many states, and in complexity, we cannot speak about them. So we speak about generalized version where we have arbitrarily large chessboard and all the pieces can have appear many, many times. Of course, in practice, when we say chess is P space hard and we speak about a fixed game, we are all thinking about the loops and this approach is blah. So in practice, everyone knows what it means, but it's not mathematically correct. We should say generalized chess. Okay, and so there are games, and there is no. So if one player has a winning strategy, then we cannot build a small certificate. I just spoke about interactive prover, but that's very powerful prover who has to solve many tasks that depend on the randomness. So still, that means that this prover has to be very clever, very fast. And in practice, you cannot use solvers for P-space complete problems. So this interactive provers don't work in practice. So if you believe that you are winning a game, then it's very hard to convince other person about this, at least in the early stages of the game. If you have few moves left, then you can try to make a game tree and convince him. So, so these are different classes. If it were true that NP equals P space, that would be a huge thing. That means that in all games, and if playing on the stock market, you can guarantee that your program will win any other competitor. Okay. Yeah, so that your program plays optimally, or you can just, it would be amazing. So so P equal to NP, it means that solver that sometimes break is now guaranteed to work very fast. That would also be amazing. If P space equals X, also amazing. If computation runs very long, then you can do it in small space. So there must be exist magical tricks to save on memory. And then memory indirectly gives speed up as well. So that would be amazing. And all these are possibilities. But what we do know is that these cannot happen all the same at the same time. So the three miracles cannot happen at the same time because from diagonalization, we know P is different from X. So at least one should be false. But nobody knows any answer. And people not even bother to try because of too many barriers. Yeah, so in the time of your life that you know all the methods and understand them and able to invent things, people know you already and give you all the money you want and whatever you wish for.
People try to solve that. Maybe it's unprovable and it's
Yeah. So there are people who try to do this, but it's very unpopular belief as well, because so the statement of this problem is an extremely weak logic and also extremely simple in this logic. If this were unprovable, it means that there is huge number, there's too many unprovable problems, and it's possible, it's a possibility, but not many people take it seriously. But yes, there are people who try to prove them. And then there is So usually the follow-up question is that if it's not provable, can you prove that it's not provable? And then so you can iterate forever. Okay. Yes. So what else do we have? We have log space. Oh, we have all the small classes. We have a non-deterministic log space, is NP. Then we have all the circuit complexities, which are between, sorry. No, they're not in the, I forgot what, what we said. So we have, so NC0 is nothing, just constant transformation. Then we have AC0. Okay, these are very simple functions. But I don't run, so there is NC1, which is an L, which is an NL, and then this was in AC1. And then we have NC2 and so on, and they are all in
P.
well, yeah, in P, indeed, yeah. Okay. Yeah, actually, I don't know so much about, so there is an open question, NC1 is equal to X. No, this is no, no. So there was,
I can prove it's not.
yeah. That's not, yeah, because it's in P, so it's no, there was an extreme open question, but I forgot.
Probably
I
if it's
only
equal
P
to
space
N.
or something,
Maybe
yeah.
if it's equal to N.
Ah, but wait, sorry, whether X is an NC1, no, it's because it's non-uniform. No, but this is the open question. So note that here NC1 is exist circuit. So this is still a possibility. It's uniform NC1, which is definitely not true.
Which of these NC1s is uniform?
Yeah, so when I write, I have to write uniform for this inclusion.
Ah,
Yeah, sorry.
okay. Okay, uniform is only needed for inclusion with N,
Yeah.
the rest of.
Yeah, and this is for long. Oh, okay, yeah. Okay, so this is what I remember. Well, we also have co-NP. So what do we know? It's also between P and P space. And yeah, we already discussed. So it's possible that co-NP equals NP, but not many people think this. And still both classes different from P.
What is known about a class of union of all time of log n to the power of k for all k?
So time.
Log to the power of k of n.
But
The
the
union-
quasi-polynomial time. Yeah, so there is question whether, so open question, is NP intersect co-NP in quasi-polynomial time? So they discovered that graph isomorphism is in quasi-polynomial time. It was 8 years ago or so, or 6 years ago. So this is QP. And then there was the conjecture, some people had conjectured that NP intersect co-NP is a subset of quasi-polynomial time because graph isomorphism.
The graph isomorphism is polynomial.
Yeah, so this was a question, but nobody has any idea.
Is it known if graph isomorphism is in this
So
intersection?
it's clearly in, so if they're non-isomorphic, so it's clearly in co-NP. But why do they say in NP? So there is Arthur Merlin proof, and then there's certain de-randomization. So there exists some randomized certificate with one round of, so with where the prover only has one round. So graph isomorphism is clearly in P space, so it has interactive proof. But it's very special because there's only one question asked to the prover. And so it's very close to being an NP.
Mm.
And so, and there's some assumption that people believe it is, many people think this graph isomorphism is an NP. And so since they believe this, they say, okay, we know one problem that's here. We know one problem that we believe is here, and we discovered it's also here, and therefore all the problems should be like this. But okay, then there was no progress after this. So yeah, so very little known.
Yeah.
And then the part that I know is even less. So yeah.
Actually, I was asking about without this 2 to the power of logarithm, just logarithm.
Yeah, but that also, yeah, log the time log to the power k of n, so sublinear time.
Yeah.
Oh, yeah, but this is very small class because you don't have time to read the input. So at least you need a probabilistic version of this. But there is a whole field of property
What
testing.
about space?
Space. Well, there is just a Savage theorem. So you have space hierarchy theorem there. And
Is it known?
well, there is
It's very similar to P, but it seems. Is it known if it's equal or contains P size? Like we know that L is in this class and L is in.
yeah, so that means that if you can run in polynomial time, you can run in very small space and nothing is known. So there is some space-time trade-off result where they say so SAT is not in yeah, the problem is that I forgot a lot myself. So yeah, there exists some non-trivial results where you both bound the space and the time. For example, yeah. So can you solve SAT in sublinear space and quadratic time, for example, or time and a little bit more than linear, say n to the power 1, 2, and then this answer is no. So there are like small trade-offs. So if you both bound the time and the space, so this called time and space class, and there is just the result. SAT is not in time n to the power, I think 1.1, and space n is 0.9 or something. So there exists some bounds here. I forgot something like this, but it's in Sipser book. There are such, I forgot which chapter. But it's already some not so easy proof. I mean, I could teach it, but it's like almost a full lecture. I'm not planning to because it's not enough people who want for me to know this. Yeah.
Oh, are there known connection with Riemann hypothesis?
There exists some special guy who proved that if some extension of Riemann hypothesis is true, generalization of Riemann hypothesis is true, then P not equal to NP. But his proof was not ready yet. So there was some other step in the proof that needs to be solved, but he thinks he could solve it in 20 years, this other step, and then he will solve extend, and it has to be positive. So extended generalized Riemann hypothesis. So yeah, but I downloaded this work, but then I understood that I should first learn other things. So it was hopeless for me. Yeah, so of course, in the beginning, if you don't speak to enough people, so I learned everything in isolation. And then I think I'm very clever, the most clever person of the room. So of course I download this. And but yeah, no, one page was enough to understand that. Yeah.
So it's very cool, the connection between a number theory and complexity.
Yeah, yeah. Okay, so it's everything I know, and it's 1 minute left. So, time for break. Next lecture will be probably about the PPT, what will also be easy for you. Probably. Yeah. Yeah, probably. Yeah. Okay. See you.